Would y'all do me a favor? Stick your name on there. I'll be back in about 5 minutes.
Lance, click my name. Tamiko, please. Thank you.
Yeah.
Oh.
Thank you, Devon.
Oh, no problem. You doing all right and stuff? Yeah. I'm back. That's a, oh, this is the part where wow. I'm not good. All right. What's all right?
I love you right now. But whenever I took it in high school, I got to teach that. It's been like 2 years since I took the class. I don't remember much.
Oh, yeah.
Yeah.
Right. Oh, I got the phone on. Who's that? Go. Pass this class together. Go. Yeah. Yeah. All right. Come on. Hasn't it? Listen. All right. Oh, you got it. I'm one. Your name is Ellen. Oh. That's it.
Huh. I thought for a minute I might have dropped because I was carrying a whole bunch of stuff to the office. Oh, yeah, you did the others for me too. Thanks. All right, so we covered most of the stuff in 2.5, but what I cut off was listing all the possible zeros. So we'll go through one of those kind of afresh, and then we'll look at two other little things. Just realize that next class, the midterm exam will be over, which is everything we've done so far. And we'll use that time to review, okay? But the exam will be open, and I think I got it open until the 20th, but we gotta check. Make sure. All right, so. All right, this one's the first one. All right, so what we want to do is list all possible rational zeros. And remember, zeros just means solutions. The reason why they call them solutions is just because of the fact that they cross the x-axis at that point where x, but when y is equal to 0. So that's why when you when we had those cubics, I was setting the x equal to 0 to find the y-intercept, and then the way you find the x-intercept is you set the whole function to 0, and then generally you factor it. I'm going to come back and put the all right. So what we do is they call it P over Q. All right. So P is this right here. This is P. P. And this is Q, the coefficient. All right. So let's list all the P's first. So what you got to do is just list all the factors of 15. And that's a matter of just one is a factor of any number. So one's always going to be it. We put plus or minus because it's a positive 15, but if you couple that with, you know, a positive, I mean, a negative 15, it's likely to be a factor, but so that we always do plus or minus. Okay, so that's all the possible factors of 15. Okay. In Q, it's a little bit easier because it's 2. So still, we got plus or minus 1. And then we also got plus or minus 2. All right, so P over Q, the possibles are, we're just going to combine those into a fraction. All right. plus or minus 1, plus or minus 3, plus or minus 5. And we're getting these by simply putting these values over these. So 1 over 1 is still plus or minus 1. 3 over 1 is still plus or minus 3. 5 over 1 is still plus or minus 5. And then same thing with 15. All right, but we got a few more now, because now we got to put the 1 over the 2. So it's plus or minus 1 over 2, so plus or minus 1/2. All right, then we can do the same thing with the 3. All right, and then we can do the same thing with the 5, which is going to be 5/2. Okay, and then the last one is plus or minus 15/2. Okay, so those are all the possible rational roots. All right, now here,
Well, I was saying, divided evenly, like 10 to 4.
well, if it was 4 over 2, then it would be 2. Yeah, these ones won't simplify any further. Now, unfortunately, the next part is, and this is the tough part. Use synthetic to test possible zeros. Now that's a lot of them, but we just have to give it a try. All right, so I'm just going to try first of all 1. And remember, we're just going into, you got to make sure they're all sequential and that none are missing. All right, so let me just test these things. We looked at a slide where they did it, and it took them about 4 tries to find one. So let's see. So bring down the 2. 1 times 2 is 2. That gives us 5. The good thing about this is that it's fast. What does that tell us? X equal to 1 is a solution. Okay? And because of this, it comes out to 0. So we hit it nice on the first try. Let's try, let's just go through in order. We're going to have, and I'll bring this up now just because of the fact that it mentions it in the next, but it kind of convolutes it. But the highest power tells us the number of solutions that we can possibly have. So we can have 4 solutions to this. But the drawback is you could have the same solution twice. You know, like if you have a perfect square of x squared minus 4x plus 4, then you would have 2 solutions that were the same. X is equal to 2. All right. So we're going to need 4 of them, but we're going to be able to, once we get it down to a quadratic, if we find one more, it's a little bit easier, then we don't have to keep testing. So let's try -1. Because the fraction ones are going to be the hardest. So hopefully, as we get along here, All right, so let's see how this works. -2. -1. This is going to be 12. And that's going to give us 3. Add these always. And -3 times. So did I do that right? Because if I did it right, then that means we got to go on.
Yes, that's right.
So always be thinking to yourself, if you get one that's not 0, have I done it correctly? Because if you somehow make a little mistake in there and you get one that doesn't come out to 0, then you're going to go on to the next one. So check and make sure we're safe. So this one, we can cross that one out. Let's make a little bit of room over here. Let's do 3. I'm gonna have to go on another page in a second, but. Times 36, 9, 18. And that gives us 7 positive, right? 21. So that's going to give us 12. 3 times 12 is 20. 36, right? And of course,
Yeah.
we don't even have to add them up. It would have to be the opposite, so 49. All right, so we can.
That's 51. 15 plus 36 is 51.
That's good. So we can count that one out because it would be 0. All right, so let's see. I'm going to.
-3.
Yeah, I'm gonna go on, but I gotta find a place to put it. I'm gonna copy this here and save it and import it over there so I don't have to write it again. One of the things that you gotta watch out for is when you copy it and you're not looking directly at something, it's easy to miswrite things. So I'm gonna copy it and then just import it. All right, so then we already knew that x is equal to 1. And I'm thinking if we get one more, we might be all right to solve this thing because, as I had said, is the highest power right there tells us the maximum number of solutions we got. Now, if we determine what the other one is, that means we got 2 of them, then we can factor it as a quadratic. All right, so let's just go ahead and do -3, right? We did 3. -6. All right. 6. -3. And still no good. It's 24, right? All right, so just keep in mind that what we've got so far, I'm just gonna do this as a. Let me go back to the original. 2x, so 2x cubed, 5x squared. So this right here, the one with the 0, tells us what the coefficients of the rest of the equation is. In other words, I'll write it out for you. So it's 2 x cubed plus 5x squared and then it was negative 6x and negative 15. So that's what we know so far. We know that x minus the 1, and remember, it's minus 1 because we're using the factor now. And so if we could solve this one, then we'll have a quadratic we can solve. Now, I probably should have done this outside of class, and I didn't really think about it, but let me try something real quick. Because that one right there may be factorable, but I wanted to check it real quick before I go ahead and go through with it. Because otherwise, because we could save some time. Yeah, okay, I'll show you something. So we could keep on going through and we could probably find them, but let me just show you something right here. The reason why I had this caught my mind is because way back at the beginning of the semester, when we had some cubics like that, you could use, they had some that you could do factor by grouping. And this one right here is factorable if we use factor by grouping. What do I mean? Well, watch. This is a little thing that's very powerful. We went over and we go over on Math 09-7. So does anybody remember how you do factor by grouping? Whenever you got 4 terms, you put the first 2 together and you take out the greatest common factor, which is just in this case, x squared. And then that's going to leave 2x plus 5. Bring down this third side and then do the same thing. The greatest common factor out of those 2 on the right, in this case, is a 3. All right. And the reason why we know that this works is because this one repeats. Now, there's one drawback to this, but they just asked for the rational ones. So one of those is this, actually 2 of those are irrational. So here's one up. Oh, let me back up for those people that need to know about the factor by grouping. So rather than repeat that same factor, we can write it like this. In other words, just write it once as this minus that. Okay? So, and I said, if we could have kept on going, checking the things, no problem. It's just that it might take us a long time. And since this one happens to be factorable, I'm just taking advantage of that. Now, there's only going to be one rational one. When we do this other one, and what rational just means when we take the square root of it, so that means x is equal to plus or minus square root of 3. So that's not a rational solution. So that's not what they want. Remember, rational just means that it can be expressed as a fraction. So once you introduce a radical, that's an irrational solution. But this one right here is. And divide by 7.2. So then here's our other rational solution. Now you can see that would have been one of them, right? Look how long it would have taken though to get it. So take advantage and check. And I probably should have checked sooner, but I wanted to just take you through the process and show you that, you know, it's a repetitive process. It's pretty quick. You can keep doing it. But once you can have got one that you can factor, you can go back to using the quadratic formula or factoring by grouping or any kind of factor and solve it. Now, like I said, once we did factoring by grouping, we found out that there was two solutions that were irrational. So in keeping with the idea of what I was talking about the highest power tells us how many solutions we got. We'll look at what all the solutions are. They only asked about these two because it said rational solutions. See? So we would have to go all the way through all of them, almost all of them to get this. And then these are the rational. And then this one is x is equal to negative square root of 3, square root of 3. All right, so are there any questions about this whole process? Like I said, we looked at it within the context of the slide where they had one, and they did one, and then I think they did 4 of them before they found one, and then they factored theirs, I believe. But here, like I said, it was just slightly different. This one I would think would be considered a harder one because it had more possible to try. That's 1, 2, 4, 5, 6, 7, 8. So there's 16 possible ones. And if we had done them all in order, we wouldn't have found the last one until we'd done the 14th one. So it just occurred to me as we was doing this to use the x equal 1, which is x minus 1 when you're talking about the factored form, times that thing. And then that allowed me to figure out by factoring by grouping to set these two equal 0. This gives us the rational one. This one gives us the two different rational ones. But they only wanted these two for the answer. So any questions about that? Like I said, it can just be a pain in the neck process. But like I said, it's just allowing you to chip away at it. And thankfully on this one, after I did the first one, I could have jumped right straight to doing that. But I tried a couple more just to see that it wasn't going to be one that I was going to find necessarily for real easy. All right, the one more thing, well, there's one more little thing I should say. All right. This is what I was talking about the fundamental theory of algebra. Like I said, to me, that's kind of hard to understand. But all that's saying is whatever you're in is the highest power or the highest degree, what they call the degree of the polynomial is. You're going to have at most that many solutions. And so that worked in this case with the x to the 4th, we had 4 solutions. And the other thing that it says that is too, in this next one, and this is interesting. Again, that's kind of hard to understand, but I'll show you what it means in a second. All right, but this is, it deals with this thing called the linear factorization theorem. And it just means that we can possibly factor out a number out of all these factors, and that number is going to go out in front. Well, what that essentially means, though, is for complex factors, or specifically imaginary factors. You remember how that works? You have the real numbers on one side, and on the other side, you have the imaginary, and both of them together is what they call complex numbers. A real number is a complex number, but so also is an imaginary number. But this is what it works, the way it works, and this is why it's kind of neat. It can save you some work. If you happen to have a solution that's an imaginary solution, like we say negative I, then the conjugate will also be a solution. So if they tell you that one of the solutions is -3, then you know this factor. And they tell you one of the factors is just plain old I. Plain old I, because remember it's x minus, then its conjugate will also be a factor. And so what you do is you set that up, give it that information there, multiply all that across, you're gonna leave the A out there. And then you're gonna use some information that they give you, which is f of 1 is equal to 8, to find out what that A is. In other words, it's a multiplier. It's a value that you can multiply through all of those. And I'll show you what we mean. So let's just look at the process and then we'll go through it. All right, so they found this just by multiplying all those three factors, but they had an A there because that A would be considered a like factor for all of them. So what does that mean is they told us that f of 1 is equal to 8. So f of 1 is equal to 8. So they put 1 in for all the x's, evaluated it, added all that up. That actually comes up to 8 as well. And this is 8 times a, or a to the n. And then they just solve for a to n. And then that means that the complete polynomial is just, in fact, only factor was 1. So we'll do with one that's got something, another number. All right, so all right, good. Sometimes the wording and the way that they explain things and definitions doesn't do justice. It makes it more complicated than it needs to be. Fine, and hence agree polynomial when n is equal to 3. I'm sorry, n equal to 3, and solutions when 0, let's say. All right. And then f of -1 is equal to 50. All right, so they're giving us 3 pieces of information and telling us that we're looking for a cubic polynomial, n is equal to 3. And they're saying one of the zeros is 4 and the other one is 2i. Okay? So let's just kind of set this up. I'm going to just do pretty much what they did in the other one. So f of x, and since what we want to find, and they call it a of n, it's multiplying everything here. So it's x, and one of the zeros is 4. And then it's x minus 2i. So that's the other one they give us. And as I said over here, the conjugate always comes along for the ride. So they told us 2i, so negative 2i will also be. And remember, that's like x minus a minus. Okay. All right, so we got that, and we're just going to multiply that across. First thing I'm going to do is multiply these two. And then I'll run through the x minus 4 once I get everything. So x times x is x squared. X times 2i is 2i. X inside is minus 2ix. And notice that the conjugates, those go away. So if you get good at this, you can skip a lot of stuff here. All right, these go away because they're opposites to one another. You remember what I squared means? Okay, so what that does,
-1.
good, what that does is it turns this into a positive 4. That's really the only effect it has. So we got x squared plus 4. Because that's going to be a -1. -4 times -1 gives us the positive 4. All right, now we're going to just multiply that out. I might need a little bit extra room here, so I'm going to just go sideways. So just form it out, x cubed 4x inside is -4x squared. And then the last is -16. -4 times positive. All right, so now we've got let me just order it for you. It's x. So the AEN is still there because we haven't used that. So it's x cubed minus 4x squared. So I'm putting in order plus 4x okay. Now, the bit of information that they give us up there is f of -1 is equal to 50. So they're telling us one of the functional values. And what we're going to do is we're going to plug that in for 50. It's -50. -50. All right, so what we're going to do, the functional value is -50. In other words, the whole thing here is -50.
How is it -50?
Because that's what it is, see? I wrote it, I didn't put the, when I wrote it down, I didn't.
Oh, you didn't put the negative, okay.
It's -50. All right, and it was -1. So we're going to replace all the x's with -1. And then we're going to evaluate it. All right, so let's just go ahead now and the AN is still there. We're going to find it soon. So -1 cubed is just -1. -1 squared is 1. 1 times -4 is just -4. This is also 4 times -1. So that's a -4. And then we're subtracting 16. So what is that? That's 25 negative. All right, so I want to write it over here. Where it looks more like an equation. So a to the n, or -25, a to the n. A to the n. So I'm just straightening it out, like how you would see in a regular equation, left to right. Because the a to the n is being multiplied by the -25, so generally you put the coefficient in front of the variable, and then that whole thing we know is equal to -50. Now, we got in one step that a is equal to 2. All right? So then what we can do is we can replace this right here with 2. So f of x so then let's just run it through there. So 2x cubed minus 4x squared plus 4x minus 16. I'm sorry, 30. Not multiplying. So 2 times 4 is 8 negative, sorry. So I'm just multiplying each of these by 2. So there is the full nth degree polynomial that has 3, degree of 3. It has zeros of 4, and it's got 2 imaginary solutions, 2i and negative 2i. And then the linear, the coefficient that was common to all of them, in other words, that we could factor out, was 2. And then when we run it back back to it, looks like that. I don't know, this is probably the last thing that's really important enough to spend a whole lot of time on, but does anybody have any questions about anything so far?
So you said with the n equals 3, that was in the very first step with the f of x, the very first one you did is because it's in 3 steps?
No, the n equals 3, remember, n is the degree, the highest, well, n is the degree of the polynomial. And the
Okay.
degree of the polynomial is the highest power that exists in the polynomial. So
Okay.
n is equal to 3 is referring to this right
The
here,
x cubed?
the cubed, yeah.
Okay,
That's the degree of the polynomial. So that means degree 3, meaning that it's going to have 3 solutions.
okay,
That's what that means. And zeros were, well, it was one of the factors was x minus 4. And then they told us by happenstance that it was 2i and negative 2i. And then once we multiply all those together, we have this one. We still don't know what the common factor is to all of them. And that's what we were determining by doing this, by them telling us that -1, when x was -1, that the whole thing should be equal to -50. And once you get all that down, you come out, boil it all down to -25 as the coefficient of the variable that you're solving for. And so that's why I wrote over here, -25, a is equal to -50, because over here was backwards. And then all it is just a 1 step to solve by dividing by the -25 to get the a alone. And then 50 negative divided by 25 negative gives us that 2. Okay. Let's see something. All right, like I said, this last part, it's not really where you determine anything. It's what I was talking to my friend, the teacher taught us more than I did. It's just basically, and it tells you what exists. It's not that you learn anything very specific like solutions. It just tells you how many you can possibly have. And so if you look at this, again, the way that they do that right there, it's just like, what in the world does that mean? And I'll just try to explain it. All right. You find the number of possible, positive real zeros. In other words, even, not even, no negative sign. That's what they mean. Positive real zeros is determined by the number of sign changes. But it's not quite, it'll tell you exactly how many, it'll just tell you more or less how many. I'll show you what I mean. All right, it can be a less number, but the less number is just by a factor of 2. So what does that mean? Let's look. So let's just finish this. And then if you input negative x in there, you remember how we did that to find an odd function? Well, the number of sign changes, then that tells you the number of negative real zeros. So I got another one to go over here, a couple if we want to, but here's the way it works. Look at the number of sign changes. 1 sign change, 2 sign change, 3 sign change, 4 sign changes. So that means we've got 4 possible positive real zeros. But we could also have 2 less than that, which would be 2, or 2 less than that, which would be 0. So you could have 4, 2, or 0. And that's all they want to know. You can't find out what they are without going through what we just finished with the synthetic division stuff and the factoring. But this gives you an idea of how many you're going to have of a certain type, in this case, positive ones. So if you just look at the function as it is, the number of sign changes tells you the maximum number you can have, which was 4 sign changes. But you could also have 2, 0, because it goes down by a factor of 2 every time. So let's just say we were looking for the number of, looking for these solutions. That might be helpful to us because we're going to look for either 4, 2, or no positive solutions. And then if you stick the negative x in there, this does it for the negative ones. All right. So because you know how when we're looking at even and odd functions, how it sometimes changes the function. And matter of fact, if a function is odd, when you put in negative in there and it's equal to the same function, then that's an even function. And then when you put it in the negative x into it and it's the same as the negative of the function, that's an odd function. Well, it's that same concept and it keeps coming back. We'll see it from time to time. All right, so after you put that in there, see that makes that a positive. It makes this one a positive because that's going to be a negative times a positive. This is going to be positive. That one's going to be positive, and that one's going to be 20. So there are no variations in sign changes, so there are no negative roots. So let's do one last one. So any questions about that? I know it's kind of it almost in a way seems like it's useless, but it could be useful in certain cases to just help you go in the right direction. Well, there's no real formula for it. If you want to write that down and it helps you, go ahead and do it. That's what I was trying to put it in some kind of human terms.
Yeah.
So basically what it is, if you look at the original equation and you look at the number of sign changes, and that's going to tell you possibly how many positive solutions you have. But it could also be 2 less than that or 2 less than that. So in the case of 4, it could be 4, 2, or 0. But if let's just say it came out 6, it could be 6, 4, 2, or 0. So then when you pump in the negative, the f of negative x, and look at the number of sign changes, then it does the same thing, but it's now negative solutions that you know about. Yeah, I mean, and like I said, I don't know how much use this is for. I mean, I could probably do all the solving the ones that we did without knowing this personally, but it could come in useful. I guess what it is, they put it in here because it's been around a long time. You notice that the name of this Descartes' rule of signs. You know, Descartes was from years and years and years ago, you know. So I think that that's kind of why it's in here, just because it's something that's been around a long time.
When I examine, midterm,
Well, let's look. All right, so if we go over the course materials and go into my math lab. Because according to this is what we're gonna go by. On the 19th, that exam will be open. All right, well, technically, we'll review anything you want to. What I might try to do is go through the little practice. We got enough time, but it's kind of hard to do that in an hour and 15 minutes just because talking and going over this a little bit, sometimes it takes more time. So you bring any kind of questions you want. And then let's see, when do we have it ending? I think it's 19th or 20th. Because we want to be free and clear on the 21st to start new stuff, because we got a lot of stuff to do here. Because also I'm finding out that somewhere in here, I thought they were doing away with that conference, but they still got it, so I'm gonna have to make allowance for that. I'm not exactly sure. I thought it was the 4th, but I didn't second. Anyway. So let's see, what is it? So I got it through the 19th. So let me just check the dates. 19th and Tuesday. So I'm gonna fix it to where it's due on the 20th, okay? So that give you an extra day.
Thank you.
When we come back though, on the 21st, we gotta hit new stuff and I'm gonna be going fast, so. Are y'all having other midterm? Because midterm is all messed up. Because now we don't have a date for midterm, because usually on a normal semester, we would have to have everything done by a certain date. So I have to go up and yeah, you got to sign the calculator. So now, I mean, because I'm not dealing with having to meet any deadlines, but still, you don't want to leave too much to the end, because as it looks, as you can kind of see, what's not that bad. The rest of chapter 2 and chapter 3 basically before the end of the year, before Thanksgiving. So we got about a month to do that, so it might work out all right. Sorry about it. But I still got to find out what happened with that conference, because they wanted, just got a thing, they wanted us to sign up for it. I was already signed up for it, but there was also a non-virtual. They were having it in New Orleans, but I don't know if they're still having that. They mentioned virtual and stuff. All right. So let's just look at a couple more of those Descartes sign changes. Like I said, this is really easy, but I don't know that it's really that useful. Let's go ahead. All right. So you say that there's other teachers doing the midterm stuff next week? All right, well, it's too bad.
A lot of my, he took it away. He said we're not doing midterms.
Well, the thing is with math, we don't have that option.
Yeah, I know, but Matthew don't, yeah.
They have the, they want a midterm and a final.
He just made us write an essay instead.
Oh, it's like English?
Mm-hmm.
All right, so, for the first one, we don't really have to do anything because for the positive ones, you just look at what you got. How many sign changes are there? Yeah. Good. So this is the one case where you actually know exactly how many you got. All right, so now we do, let me just put up here, this is f of x. Back years ago, they didn't have like a group final exam, and then they caught on that whether like they didn't trust us or something, you know? So I don't know. Now you can't get away with that. So now we're just going to replace all the x's with a negative x, and that's what is called f of negative x. So this is going to be another, still negative because it's negative x times negative x times negative x. Anytime you got an even, I mean, an odd number of x's, it's still going to be negative. This one's going to be positive though, because negative x times negative x is positive. All right, how many sign changes? So there's one, two, three. And two less. Okay, so that's really all there is to it.
So where's the 2 on, because like at the top you have x to the third, 2x squared. Where's the 2 on this one? Oh, it was replaced?
Well, no, it just, you can put it back there.
Oh, okay. All right.
That's not the number that matters. I just miswrote it, but it's the changes. As long as they had the positive right, but yeah, I meant for the two.
All right, I just wanted to make sure I was,
Yeah,
okay.
when you, it was me. All right, let's just look at one last one and then we'll be done. So this ends, like I said, 2.5. Okay. Five x cubed minus 3. 3x squared. So how many sign changes are there? There's 3. So 1, 2, 3. All right, then you can just do the other one, the f of negative x. So this one's still got, this one's gonna make this one negative. This one's gonna stay the same. Don't move that down. Should have. Do it like that, but it's still gonna be the same. So this is gonna be negative 5x cubed. And this is gonna be negative 3x. Yeah, negative 3x is gonna be negative 3. That was negative x. So this is gonna be negative 3x, like it was, and minus 1. So how many sign changes? No sign change. So there's no negative roots.
2, huh? No,
You see any sign changes there on that one that is wrote?
the -5, right?
Okay, let me.
The plus 3 was changed to -3x, so
Okay,
it's,
hold on.
okay.
Because I think you, not seeing what the sign change is. All right. The sign change, like for example, in the original one, see here, it was positive, it changed to negative. That was one sign change. From negative to positive is another sign change. And then from positive to negative is a third sign change, right? Okay, now that tells us the positive ones. I should have put positive there. All right, so when I put the negative in there, that's the, see, that's the, what we gotta do here to find those. You put negative x in, just like you did for, to find the odd function.
Mm-hmm.
All right, and then you just evaluate it. So negative x cubed, still negative, so it makes this positive negative, right?
Mm-hmm.
All right. The negative squared is going to be a positive x squared, so that negative stays negative.
Mm-hmm.
This one is negative x times 3, that makes this a negative 3x, and then the negative one isn't affected. So all of those are changes. I mean, all of those signs are the same, so there are no sign changes. So that means we've got no negative real roots. Okay? So the sign changes is after you've evaluated it for the negative x, or the second part is. First time you just look at it as it is, and then for the negative roots, you plug in negative x and evaluate it. Just like we did for odd functions, odd and even functions. All right, so if you got any questions, by all means, ask away.